So please, Pavel, just introduce yourself.
So hello everyone, I'm Pawel Kusiński, so impossible to pronounce for Casio. And today I'm going to talk a little about persistency on serverless, so one of the attack vectors on function as a service. So I think we can start. I won't be boring you with my titles. So what are we going to do today? We are going to achieve persistency on vulnerable Lambda and cloud functions, so GCP and AWS. I will show you a live demo, live exfiltration of the data from the both of them. This method is nearly undetectable after execution. So let's see how it's done. Let's start from some basics. I will explain at the beginning why I even chose this topic. So my main inspiration was Yuval Avrahami, and now I hope I'm pronouncing it right. He's from Unit 42, and he was the first one to deep dive into the topic of serverless. He did this on AWS Lambdas already. So I thought that I will continue his work. Second argument for me was that serverless is really widely used by corporations. A lot of companies are introducing the function as a service into their products or experimenting. So in the nearest years, we'll probably see a lot more of attacks on serverless. For those who don't know what is even a serverless function, it's something where we can upload our code and we don't have to deal with managing the server. So we are only just looking at our code, we are only managing our code. We don't have to worry about deploying it, about securing the environment, etc. So it looks nice, it looks great. But what if there is a vulnerability in our code? What if that vulnerability would be an RCE, remote code execution? And okay, some of you which are into security would probably now say, but Pavel, RCE is so rare that nobody would do this. Why even care? I think we should care because, especially in last years, we've seen a lot of attacks on developers, on package managers. So we've got, for example, typo squatting, dependency confusion, account takeovers of package manager, of libraries, and a lot of stuff where we can just introduce the vulnerable code to one of the packages we are using. Even not so long ago, there was a malicious package in Python libraries, one of the widely used ones, CTX. And funny thing, it was stealing the keys from AWS. So let's go from the start. We've got this beautiful Lambda, which is processing some data, which we are sending. And the processed data is going to be saved on some database, in this case, DynamoDB. Let's say our DevOps or administrator knew how to do his stuff, and he created a role which can only write to DynamoDB. So theoretically, we cannot read the data saved on DynamoDB. But what if we will introduce our exploit into the Lambda itself, or the environment where the Lambda is executed? Then we'll be able to exfiltrate the data live, so we don't need to have an IAM role. We can just read the data. I'm going to cover some topics of serverless infrastructure. to get to the core of everything. First thing is a cold start, or also called cold boot. It's a happening. It happens when we first call our Lambda or cloud function. So the first execution is usually really slow because the environment has to be boot up. Okay, that's great. Consecutive calls are faster. Every next call will be executed a lot faster because environment is already up. So our file system probably persists, but it happens it is only frozen between the calls. And at least for me, it was mind-blowing because I thought that serverless functions are like volatile ones. So after the news, we don't have an environment. Why do we need one? It works like that. So we have some user or service which is calling our Lambda. Then the invoke service, the one of the backend AWS services, is looking for the machine to execute our function. Because there isn't one, he calls a Firecracker to set a micro VM, micro virtual machine. Firecracker is a software created by AWS for booting these micro VMs really fast. It, of course, is on sandboxed environment, so it should be secure, not so secure as I will show you. And of course, it executes the Lambda function, which gives us our response. That's the first execution. In case of consecutive calls, the process could be really simplified because invoke service calls Firecracker, which has the machine, so it could be simplified like that. It's really fast. In case of GCP, we've got really similar approach as we will be using also the containers, but this time with gvisor. That's also a security sandbox, so nice. The next thing is something I called control process because I didn't found an official name. So what is that? In case of AWS, our environment, our file system looks like that. So we've got some bootstrap process on the file system, which talks with the init process. Bootstrap is communicating through HTTP with the init, and it wants to get the next call. So he sends the next request and awaiting a response. Slicer is some process outside of our VM. We don't know what it is, but the slicer sends event to the init process, which then sends it to the bootstrap with the invoke ID, which will be important in a moment. The event is then sent to our code, and it is executed, and then response is going back to the init process. And for the process to end, we have to send an invoke ID to init process. With GCP, the whole problem is really simplified, as GCP thought that they can just boot up a web framework. So they are using Flask in case of Python language. In case of other languages, they are using similar web frameworks. So they are just routing all the events to our function. They are just dynamically importing it. Really pretty simple, nothing to comment there. So why persistence is possible in this semi-volatile environment? First thing, really we don't have volatile file system. That's at least some for a few minutes because the file system persists for like 5 to 15 minutes. In case where we'll be pinging the system all the time, the file system will persist for hours. There won't be a need to destroy the first one and to boot up new one. we've got nearly writable file system, as we can access the TMP folder, and we also can access the memory. And what's the interesting one, the control process is inside of our container or micro VM. So let's imagine, in case of AWS, let's send some malicious event to the vulnerable Lambda. Our malicious event, so our payload will boot up a new bootstrap. And now the question for at least offline guys, we have to get invoke ID. Any ideas how? Yeah, there is on the there is invoke ID on the file system, but how we can get it? We aren't root. We have to remember that. Okay, so first thing which comes to mind, when we are part of the process, because we are executing from our Lambda, we can just look at the stack. We can just import inspect library in case of Python, or other alternatives in case of other languages, and search the stack for invoke ID. It will be here. In case of being a sub-process, when Lambda executes our code in another process, we can regex through the memory, through the prods, because we have access here. But there is a really simple method which is undocumented and really funny, because if the last process didn't end, the last bootstrap didn't send back invoke ID, we can just request it again and we'll obtain the same invoke ID again. So init process just going to send us the correct one, and we can end the process with our evil bootstrap. So now we'll have a situation where the old original bootstrap is still waiting for the response in this frozen sad state, and our bootstrap is just communicating with the init process and our server. What about GCP? As I said, there is some dynamic imports, so I thought, why not to use this little monkey, or the process called monkey patching. That's the dynamic override of definition of the function. So we are sending our malicious payload to the vulnerable cloud function, and we are just going to override the routing function to now execute some of our code. So let's go for a demo. In my demo, I will have this piece of code. This is a vulnerable function. So we've got here a vulnerable YAML library with a remote code execution. And I've got backup videos, but let's hope that I will be able to do this live. I don't have duplicate screens, so it's not gonna be easy for me, but let's try. And I've got internet, I hope. Or not. I'm live? Okay. That's funny thing. So maybe let's do a fast reboot. Live demo problems as always. Let's give it a moment, and if there will be still a problem, then we'll go for a video. This is a meme question, I think, from my presentations. I was too lazy to test the Azure functions. I've got this planned for the next month. So I'm not sure how it works in Azure. I can't be sure, but I really think it works like that. That's funny thing. I've got one other idea. Wait a second. I hope I won't disappear because probably I have to connect to my VPN to get access to my server. No, life is more emotional. Give me like 1 minute. It will work. You see, like everything not working is nice now interesting. And okay, yeah. Okay, so we have to go with the video because my VPN it cannot connect from guest Wi-Fi here. So sad. So let's say at the right side of my screen there is my own VPS server, which will host the web server for hijacking the events. On the left side, we've got the attacker console, which will be sending the malicious payloads, and normal user, which will be sending some demo data, which will be hijacking. Let's go with that. So if I remember correctly, let's see our YAML. In our YAML, we've got some basic data like name and email, and we are sending it to the Lambda function and getting the success. So everything good. Let's start some listener on our server and create our YAML payload. I will show in the moment how it looks like. This is just a shortcut for creating a YAML file from our payloads. Let's send it, and as we will see, now the response is a little bit longer, that's intentional, and we've got different output. Let's try sending the data again. And after a moment, we can see the data got to our server also. We will also send the second payload to verify the persistency of this malicious payload. And as the last one, we've got our data. So, as you can see, I've created a YAML file from two files, from Switcher and Evil Bootstrap. So let's go into that. We've got this Switcher code, and don't worry, you don't have to read this all right now. We'll go line by line. So at the start, we are just decoding our Evil Bootstrap, which was part of our payload. We have to save it somewhere to be able to execute it. And we can just send it to the TMP folder. But in case if TMP folder would be somehow blocked, you can also create an anonymous file by syscall mmfd and saving the bootstrap just in the RAM memory. It's not a problem. Then we have to obtain our invoke ID. So as I said, we are just creating an HTTP request to the init process. And AWS is a really good guy because URL lib3 is pre-installed on every Python environment. Nice for us. We don't have to go into the sockets. Then we are just executing our new bootstrap. And our bootstrap whole Bootstrap is just a copy of a normal one. The code is on the GitHub, or we can download it from a normal Lambda function. We have to add some lines of the code. So first thing, the main for execution. We have to start the process and send the invoke ID. Then we have this beautiful piece of the code, which you don't have to worry because only this one line matters for us. And this one line, which I added, is just sending the incoming events to our external server. We have just to hard code our IP. And as I said before, we've got our leap. Great. Let's go fast with GCP. The same, you know, what is on the right, on the left side, the same look. We are sending the normal YAM file, creating the evil one, sending it, waiting for execution, starting listener, and now we'll be sending YAML again. Simple as that. So what was the change in the code? Switcher, the same thing. We are just saving it on the file system, and then happens something different, because this time we are monkey patching. So we have to import our saved function, we have to import user function, and we have to do this all dynamically because we are inside of the executed code. So we cannot just use import library. That would be too easy. So we can go into the documentation how import in Python works and copy most of the lines of importing the files, where we have to get the paths for our code. Then we have to load it and import it. So build the modules, append it to the environments, to our sys, and also execute it our namespace to be able to get all of the variables or everything out there. And for all of you which are reading the code, you are probably interested from where I've got this up variable. So because we are part of the process of the original one, we can just import it from the original Flask one. So we are getting the context of the Flask. And because of that, we can overwrite the function. So we are just overwriting it. Simple. And our new evil function is just sending all of the events again to our server. This time GCP was a little bit, I would say, smarter. We don't have URL leap, we don't have requests. We have to go with clear sockets. And that's all. That's all. We are just giving there our exfiltrate data and our little socket implementation. You can do this by yourself. I've uploaded everything to my GitHub. You can set up everything with Terraform. That's like 1 minute, 1 comment, and then send your own payloads. What about the external process? As I was saying, in AWS, that's not a problem because invoke ID could be obtained by creating a HTTP request. In case of GCP, I didn't find any way to do that, because in case of being a part of a process, we can connect to the Flask namespace and overwrite the routing function. In case of being a sub-process, we don't have this possibility, and we don't have any access on the system level to deal with the process memory. We cannot like fuzz it or overwrite it or anything like that. At least for now, I didn't found any way to do that. So GCP is a little bit more secure. Let's go to mitigations and detection. So what do you think? Any ideas how we can secure it? That's interesting. Yeah, that's interesting idea. I've discussed it with few people, but we think that wouldn't be possible because it would limit the possibilities of the functions itself. Because, for example, using the file system is one of the functionalities which cloud providers want to give us. For example, we can use this for optimization for some AI data learning. Like we can save something on the file system and minimize the execution time, where on the function as a service we are paying for execution time. So that's important one. In case of both providers, we can go with our virtual private cloud. So we can just deploy our functions in our own private subnets. We don't have to deploy it publicly. In case of AWS, we can go without NAT gateway, so then the function will be fully private. It won't have connection to the outside world, but also outside world wouldn't be able to connect to our function. So in case of some private data modifications or something like that, like external backend process, that's good enough. That would just work. In case of GCP, we can go with the same thing. So it's called then whole traffic routing and also without NAT gateway. But the problem is when we want our function to be visible publicly. In case of AWS, we can go with implementing security group, or rather configuring security groups to not allow any inbound connections, because security groups are stateful. All incoming connections will also be possible to response, but Lambda won't be able to create a new connections. So implicit deny. In case of GCP, I don't know why, but there we have to create an explicit deny rules. So we have a little bit more problem because it won't work as easy as in AWS, but it's also possible. So we can just, in case of AWS, create rules like that. We can open for inbound, close for outbound. And my little evil bootstrap will just show that connection timeout. The same with GCP. We are creating the deny rules and obtaining timeouts also. But if you think about it, that we have RCE, or for example, comment injection, it is still possible to evade this. Like, we can just modify our evil bootstrap to store all of the events on the file system in the temp folder. And then, like after 10 minutes, we can send new payload, which will read it and set it back in the same connection, evading all of our security group rules. So really, it isn't possible to deploy publicly vulnerable function and make it secure. Or as one of my friends said, we just have to don't deploy vulnerable functions. It's that easy. So how about detection? That's also a funny thing because it's really hard to do in case of having a vulnerability like that. We can try with creating some alerts based on execution time. As you saw, the execution time of the function in case of our payload was a little bit longer. So when we've got some statistics and we can create some, based on this, how long our function executes normally, then probably we could create some alerts, but there would be a lot of false positives. At least one problem with AWS, one problem with the connection, and our alerts will be like, oh no, we are hacked. And that would just some, I don't know, some fish going through the lines under the sea. We can go with SDLC, which I think is the best and only solution. Like, we can just shift left. So secure development lifecycle, we can secure our continuous integration and development process pipelines. We should discuss before deployment what are the risks, what we need to use, and verify if libraries which we are using and our code which we are deploying is secure. And also implement some verifications on CI/CD that nobody tampered with our code or with some libraries. We can just verify, for example, SHA hashes. I've got also an idea of implementing defensive layers. On AWS, we are able to create something called layers on Lambda functions, which are something like other containers. And there was an idea of implementing a layer which would verify the file system if, for example, nobody tampered with it, or verify the bootstrap or our code. But as long as it is possible, I think that's a lot of work for developers. Like in case of every function, we'll be needing to implement some defensive things. It will also be probably not so good. It could be also evaded probably. So why to lose time? I'm not seeing a company which will be paying for this method. Like, hey, we want 10 days to implement this layer. And what will be the result? Maybe it would work. Sorry, no. We can also analyze flow logs, so our network traffic. But it's also not so ideal because, yeah, we can see that, for example, our function is connecting to this one IP 10 times a day or million times a day. And that's probably something not good. But we can just create some little botnet and rotate our IP. We can create new machines, so it won't be flagged as some bad ones from Virus Total or some other companies securing the internet. So I don't see flow logs to be good for this one. And at the end, I wanted to talk a little how we can research these topics. So we've got documentation, especially AWS documentation, which is good. I would say there is a lot of information, but the only problem with AWS documentation is that you won't find anything if you don't know what are you searching for. Like, really, you cannot go to the Lambda documentation and find the information about Firecracker, about the file system and everything, because I don't know why it's hidden somewhere. But if we will search for Firecracker, there's a lot of stuff about it. In case of GCP, I got a lot of problems because documentation is really quiet about backend. We can also search for official events, official blogs. There's also a lot of information. We can just Google it. It's that simple. Or we can deploy our Lambda locally, whole code of which is executed on the micro VM. So the bootstrap process, etc., is on the GitHub. It's an open source. And you can also just try it on real environment, because it's not a problem. Oh, that was a GIF, which is not working. Whatever. Because we can just create a function which would be something like a shell over HTTPS. In case of reverse shell, it would cost us billions of dollars because Lambda is priced based on execution time. So reverse shell is a bad idea. But we can just create an HTTP shell. So we will be sending in HTTP request our commands, and in response, we will be getting the output. And I will try my luck with this one because I don't have to have VPN connection, probably, to show you how it works. Let's go to some weird folders. Okay, and there should be my shell and my URL. Great, and we've connected to our Lambda. I've implemented something like a shell, and we can just send our comments to get some information about laying file system there. We can also, for example, send the files, like upload it to the Lambda file system. We can download it, so we can just download any file which is on the Lambda file system to analyze it. It's pretty nice stuff. And as I remember, it costed me like $1 after a month. So great thing. I could recommend it. Where is my mouse? Here, great. You can also download it from my GitHub. And yeah, that one is based on Juvals. I've upgraded it a little for my own experimentations. Thank you all for your time. And let's go with some question times.
Basically, I saw your showing class, and it's very common nowadays with template injection, which is exploiting this class vulnerabilities as well. And when it happens, usually we still keep in this session at the same time. You want to say no? Okay. And then this class will be executed because basic Python stuff happening in there. And we're still able to import Python libraries that will be available there. I don't know, I mean, it will depend on the environment. And still having the same reverse shell or anything using simple template injection techniques. Just adding one comment, like really good work like that.
Yeah, thank you.
Great. No questions. Also from online people. Pawel Kusiński.
Kusiński. Nice, nice. You got that.
So great. Thank you.
Thank you also.